Today, we are diving deep into one of the most fundamental concepts in all of quantum computing, the quantum gate. If you think of qubits as the building materials, then the gates, or the tools and the blueprints, they're the instructions that let us build something incredible in the quantum world. So let's really get into this. We hear all this buzz about qubits, right? These amazing little units of quantum information. But just having them isn't enough. It's like having a brand new supercomputer sitting on your desk with no keyboard, no mouse, no software. The big question, the one we're tackling today, is how do we actually command them? How do we write the programs of the future? All right, here's our game plan for this explainer. We're going to start with the basics of controlling the quantum world. Then we'll open up the essential toolkit of gates. After that, we'll see how to create quantum connections, how to build those into actual programs, and finally, we'll hit on the real-world challenge that everyone in the field is facing. So, let's kick things off with our first section, controlling the quantum world. This is all about taking the raw, mind-bending potential of a qubit and figuring out how to give it precise, meaningful instructions. And the answer, as you've probably guessed, is the quantum gate. You can think of them as the verbs of the quantum language. You know how your phone or your laptop ultimately boils every single action down to a simple set of and, or, and not gates? Well, it's the same idea here. Every quantum computation, no matter how complex, is just a sequence of these fundamental quantum gates. They are the instruction set. Okay, time for section 2. Let's open up the toolbox and look at the basic toolkit. We're going to start simple with the essential gates that work on just one single qubit at a time. First up, we've got the X gate. This one is probably the most straightforward of the bunch. It's basically the quantum version of a classical NOT gate. If your qubit is in the 0 state, the X gate flips it to 1. And if it's in the 1 state, you guessed it, it flips it right back to 0. Simple, clean, effective. The absolute best way to picture this is just a simple light switch. Think of the off position as the 0 state. That's just our label for quantum 0. And the on position as the 1 state. The X gate is literally just the action of flicking that switch from off to on or on to off. That's it. All right. Next up, we have the Z gate. And this is where things start to feel a little more, well, quantum. This is what we call a phase flip gate. Now, if your qubit is in the 0 state, the Z gate does absolutely nothing. But if the qubit is in the 1 state, it flips its phase. So what on earth does flipping the phase even mean? It's a really subtle move. It doesn't actually change the odds that you'll measure a 0 or a 1. Instead, it changes the qubit's relationship with other qubits. A simple way to think of it is that it's like sticking a negative sign in front of the 1 state. And this little trick, this subtle change, is an absolutely crucial ingredient for making quantum algorithms, like Grover's search, actually work. And now for the headliner, the Hadamard gate, or just H-gate for short. This one is, you could argue, one of the most important gates of all, because this is our magic wand for creating superposition. It takes a qubit that's sitting there as a definite 0 or a definite 1, and it puts it into a perfect 50-50 mix of both states at the exact same time. I love this analogy. If a qubit in the 0 state is like a coin sitting heads up on a table, the Hadamard gate doesn't just flip it. It flicks it into a perfect spin, right on its edge. And while it's spinning, it's not heads and it's not tails. It's in a superposition of both. This ability to explore all the possibilities at once is the secret sauce behind the immense power of quantum computers. Okay, so we know how to play with a single qubit, but the real magic, the real power, happens when we make them work together. And that brings us to our third section, creating quantum connections, and the superstar of this section, the CNOT gate. The CNOT, which stands for controlled NOT, is our first 2-qubit gate, and its logic is actually beautifully simple. It has 2 inputs, a control qubit and a target qubit. The gate just looks at the control qubit. If and only if that control qubit is in the 1 state, it then performs an X gate, our little light switch flip, on the target qubit. If the control qubit is 0, it doesn't do a thing. It just lets the target pass on through unchanged. And here is the big takeaway, the thing you absolutely have to remember about the CNOT gate. This gate is the fundamental tool we use to create entanglement. This is how we link the fates of 2 different qubits together, turning them into a single connected system, no matter how far apart they are. It is, literally, how we make qubits talk to each other. Now that we have our single qubit tools and our 2-qubit connector, how do we put it all together to build something useful? Well, that leads us right into section 4, building quantum programs. It really helps to think about this as a kind of hierarchy. At the very bottom, you've got the gates themselves, right? Your individual instructions, like X, H, and CNOT. When you line up a bunch of these gates in a specific sequence, you create what's called a quantum circuit. And that circuit is basically the blueprint for executing a bigger idea, a quantum algorithm. I really like this way of thinking about it. If the gates are the letters of a new kind of alphabet, then the circuits are the words we spell with them. And by arranging these words in just the right way, we get to write a whole computational story, a story designed to solve a really complex problem. So far, this has all been pretty clean, all on paper. But what happens when we try to actually build these things? Well, that brings us to our final and maybe most important section, the real-world challenge. Here's the hard truth. Building and controlling these gates is incredibly difficult. Real quantum computers are ridiculously sensitive to noise, to vibrations, to tiny temperature changes. This means that when you try to perform a perfect X-gate flip, it might not flip perfectly. It might be off by a tiny fraction. And these little gate errors, they add up, and they can completely wreck your calculation. And this brings us to a term you will hear constantly in this industry, gate fidelity. It's the key metric. It's basically a score from 0 to 100% that tells you how close your real physical gate comes to the ideal, perfect version from the textbook. The entire engineering battle in quantum computing today is about pushing that gate fidelity number from 99% to 99.9% and then to 99.99% and beyond. Which leaves us with a final, fascinating question. We have these amazing, powerful ideas for gates, but in the real world, our tools are imperfect. This is the reality of what everyone calls the NIQ era. That stands for Noisy Intermediate Scale Quantum. So the big question, the million-dollar question really, is this. With these powerful but flawed machines, what are the first truly world-changing problems we'll be able to solve first? That's the challenge, and that's the huge opportunity for everyone working in this field right now.